Thank you. It's a pleasure to speak in this special anniversary session. So I want to start by making a few general remarks about the period 30 years ago, and in particular, two developments that gave new pathways for exploring quantum field theory. One was simply new examples, and in particular today, these topological examples. And so these papers of Witten had examples in gauge theory, in Sigma models, in gravity, which we heard about earlier. And these are, of course, full-blown physics theories, full-blown quantum field theories, but inside they have a topological piece, a topological sectors and variants that one can define. And at that time, Witten also introduced a three-dimensional field theory that was purely topological, that captured not only the Jones invariants of knots and links, which had recently been invented, discovered, but also gave new invariants of knots, links, and three manifolds. And I'll just say in passing a little bit of a puzzle that arose at the time with that paper, because on the one hand, Witten's starting point is this beautiful Chern-Simons functional that we knew and loved in differential geometry, the secondary invariant that was introduced by Chern and Simons in the early 70s. And on the other hand, these invariants were also discovered by Reshtikin and Turayev, who had a very different starting point, this algebraic data of a Hopf algebra, a quantum group. So depending, you may like one or the other better, but the question is, how is there one story that has both of these ingredients? How do they fit into a single story? They seem very different at the time, and very different starting points for constructing what was evidently from the formulas, the same invariants. So one aspect, as I said, are these examples, and the other development that opened new avenues into quantum field theory was the advent of an axiom system, just writing down a simple axiom system that describes what a quantum field theory is. So that's very different from giving examples. The axiom system does not tell you how to construct examples, much in the same way that when we teach a first course in analysis, we say that the real numbers are the unique complete ordered field. But saying the words complete ordered field doesn't tell you what a real number is. And so this was introduced by Graham Siegel in the context of two-dimensional conformal field theories. And as I say here, having a good definition is something that can really transform. And having the combination of this definition or axiom system together with new examples was quite powerful. And of course, eventually that combination leads to theorems and lots of developments. So shortly after that, Atiyah wrote down axioms, adapting those to the topological case. And the paper that he wrote is here, and notice that it's dedicated to René Thom. René Thom, in his 1954 thesis, had kind of revolutionized the study of cobordism by relating it to homotopy theory. And anyway, as Tia writes, cobordism plays a key role in these theories, and indeed in the axiom system. So I want to describe some of the background here, something that we'll need in this lecture, by discussing what's really the simplest non-trivial quantum field theory, which is a gauge theory built from a finite group. And so here you see this is the gauge theory, and in this axiom system, the field theory is a map. The domain of the map is a category of manifolds built on Bordism. So the objects of the category, here we're doing it in dimension 3, the objects are closed two manifolds with no extra structure. They're unoriented two manifolds. And a morphism from a two-manifold Y0 here to a two-manifold Y1 is a three-dimensional compact manifold with boundary, and the boundary is written as the disjoint union of Y0, which in this picture has two components, and Y1. And so on the boundary, we give a little arrow that tells us whether that boundary component is in the domain or in the codomain, whether it's incoming or whether it's outgoing. And of course, we compose by gluing Bordisms. So that's the domain, and the codomain is the category of complex vector spaces and linear maps between them. So a map from here to here is a linearization. You can think of it as a representation, and that's what a field theory is. It linearizes this nonlinear structure of manifolds. And here we have topological field theory, so we have no continuous fields, no metrics, conformal structures, or what have you, and even in this example, no extra topological structures such as orientations or spin structures. And so given a finite group G, there's a simple finite gauge theory. And how do you construct it? Well, it's constructed by the usual kind of path integral. So attached to any manifold, and here we're going to have 2- and 3-dimensional manifolds, we have a space of fluctuating fields, meaning the ones we're going to sum over. And that's the space of G bundles. G is a finite group, so these are just Galois covers. There's no connection. There's a unique connection, if you like. So there's no extra connection that's necessary to specify. And there are maps between such bundles, and so they form a groupoid. And so that's what we want to sum over. And to get the invariant of a closed 3-manifold, we just count them, but we count them weighted by automorphisms. For a closed 2-manifold, we could think of doing quantization. We take functions on those bundles. And if we have a Bordism in general, then these fields form a correspondence diagram. I take a field on X, I can restrict it to the incoming boundary, I can restrict it to the outgoing boundary. And so we get that diagram, and we want to linearize the diagram, which we do by push-pull, meaning we take a function here, we pull it back, and then we push it forward. That push forward is the path integral, which in this case is just a finite sum. And so if you do that, then it just follows quite formally that you get the structure of a field theory, that you get gluing and so on. And so this is the construction of this finite gauge theory, which, as I say, is really the simplest field theory. It could be thought of as the simplest example of this 3-dimensional Chern-Simons theory. But it's also a simple example of Yang-Mills or anything else. It's just a finite group. So we want to go further, and I want to think of this canonical quantization, how we get the space of functions when I have Y, which is a closed surface. I want to think of that as actually also a finite sum. So when we have a 3-manifold, we sum the function 1, normalized by the automorphisms. And here we're going to sum the function which is not numerical valued, but rather vector space valued. We just take the function, which is constant value C, and we sum it up. But again, we take into account the arrows, which means we take the invariants. So if you like, there are invariant functions, and that's, of course, what the answer is. So you can think of this canonical quantization as also a kind of path integral in the sense that you're summing. And that tells you what to do if you want to go further. And by further, I mean we're going to get invariants of lower dimensional manifolds. So if we just have 3- and 2-dimensional manifolds, then the vector space we attach to a surface is not local on the surface. And the strong form of locality in field theory would tell us that that should be local. We should be able to construct everything just from little open sets. And if we want to write an equation about those vector spaces, we have to be in a linear category. And so we sum vect, or if you like, take invariant sections. And so what we attach to the circle is then a linear category. And it's the category of vector bundles over the groupoid of fields on the circle. So what do G bundles on the circle look like? Well, if we fix a base point and we go around the circle, we get a monodromy, which is an element of the group G. And if we change the base point, it conjugates. And so the groupoid of bundles is equivalent to the groupoid G acting on itself by conjugation. So here's the picture of G acting on itself by conjugation for the symmetric group of order 3. And what we attach to the circle is this linear category, which are the vector bundles over that. So they're equivariant vector bundles over the group, equivariant for the conjugation action. So the irreducible, the simple objects, are given by a conjugacy class and a representation of the centralizer. So now I can tell you the solution to that puzzle I started with, where the Chern-Simons invariant came from the Chern-Simons functional on the one hand and from Hopf algebras on the other. So we could do a variation of this finite group theory which won't occur in the rest of the lecture, but in this slide, we can twist by a cocycle. That's the Dijkgraaf-Witten introduced that. And so when we sum, we weight by the cocycle, which is the exponentiated action. And so we get this weighted sum on a closed 3-manifold. On a closed 2-manifold, we get sections of a non-trivial bundle. And what do we get on the circle? Well, this groupoid gets a central extension in the sense that there's a line attached to every arrow in the groupoid, and these lines tensor when you compose the arrows. And so instead of getting equivariant vector bundles, you get a kind of twisted version of an equivariant vector bundle. And that's the category that you attach to the circle, but that category could be thought of as the representations of the path groupoid. Just take the vector space on the arrows, but instead of taking the vector space on the arrows, you take the sum of these lines. So it's a twisted version of the path groupoid. And that turns out to be a Hopf algebra, and that follows from the field theory because of the structure of the circle, and you get a multiplication and so on in the familiar way. You get a braided tensor category, and that braided tensor category is in fact representations of a Hopf algebra by the work of Tanaka, as we learned last night from here. So that's the solution to how we can see the classical Chern-Simons functional. That's a starting point, and then you compute a Hopf algebra in this extended version of a field theory. Well, once we've gone down to the circle, we want to go fully local, so we want to go down to a point. I'm sorry, before we do that, I wanted to say another aspect of extending down to the circle, and this was beautifully described in the ICM lecture from 2000 of Anton Kapustin. So, namely, you have extended operators. And so in this theory, if we have a 3-manifold and we have a loop, and let's suppose that the loop has a framing on its normal bundle. So each normal space can be identified with the standard vector space, R2, and therefore the link at each point of the unit circle can be identified with the standard circle. And so we're going to get a line operator in the theory by taking what the theory attaches to a circle, this category, and taking an object in that category. And so we can think of the category attached to the circle as parameterizing the possible line operators in this theory. So that's another way to think about this extended field theory. And in this case, we have two special ones, which are the Wilson loops. Those are the usual formula for the Wilson loop given by a representation. And in terms of the vector bundles here, those are the ones that are supported just at the identity. So those are given by a representation of G. And on the other hand, there are the 't Hooft loops. And those are the ones where these centralizers all act trivially. So the irreducible one is just to have trivial rank 1 bundle supported on a conjugacy class. And that conjugacy class then twists the notion of a G bundle around that circle. Okay, so finally, if we want to say this in terms of the axiom system, then now we can say that our theory is a map from 1, 2, and 3 manifolds. So the 3 manifolds now are allowed to have corners, and the target now has to also have 3 layers. It's a 2 category, namely the category of categories. And so what does that do for us? Well, for example, supposing I have a 3 manifold with boundary, now we could have a loop operator which ends on the boundary. So how does that look in this axiom system? Well, if we cut out the tubular neighborhood, then you see we get a manifold with corners. And that manifold with corners is a diagram like that in the Bordism category. It's thought of as a 2-morphism. So here we have the 2 circles. They're bounded on the one hand by this cylinder, and on the other hand by the complement of these 2 disks in the boundary. And then the 3 manifold is a map from the boundary, that cylinder, to that. So that's what's encoded in that diagram. And now if you apply the field theory, then you can analyze what kinds of operators you get here. So we have not only loop operators for closed loops, but if we have a boundary, we also get operators for paths that end on the boundary. All right, so finally, if we want to go to full locality, then we have to, it's clear what the domain should be. We should now have 0, 1, 2, and 3 manifolds and allow all sorts of gluing and corners. But what should the codomain be? What kind of invariance? And in general, in field theory, there's no good universal choice for that codomain. But in this case, there's a nice choice, which is the collection of tensor categories. So if we take tensor categories, they form a three category, as it turns out. And a map between two tensor categories is a bimodule. So in the same way that algebras, you have a Morita category of algebras, you can have bimodules and think of those as a map between algebras. We can think of tensor categories in that way, categorified version. And so there's a good algebraic theory of tensor categories that's been developed, and there's a nice book by these people. And Douglas, Schomer, Priest, and Snyder developed the theory in this kind of categorical way that's adapted to topological field theory. So if you take this gauge theory, now we could compute what you get on a point by somehow quantizing the bundles on a point. There's only one bundle, the trivial bundle over a point, but it has automorphism group G. And if you sum that in the right way, what you get is a tensor category that's a categorified version of the group algebra. So it's the group algebra of the group whose coefficients are vector spaces. In other words, it's just the collection of vector bundles over the group. And how do I multiply vector bundles? Well, I do convolution, which means that it's this formula. It's really pushing forward the vector bundle, two vector bundles under the multiplication map. So that's the tensor category that you would attach to a point in this gauge theory. So the main deep theorem in the subject is called the cobordism hypothesis. And it says that if you have a theory that's fully extended, then it's determined by what happens on a point. So this encodes this strong form of locality that you can build everything starting from disks, if you like. You can glue everything together from disks. But the theorem doesn't just say it's determined by a point. It says given the right data attached to a point, we can actually build a theory. So there are various decorations here. The FD is some finiteness condition. So in a topological theory, the objects you attach satisfy strong finiteness conditions. And this O3 is saying that if we want to have the theory on unoriented manifolds, then we need some kind of invariance. But as I said, we can run it backwards and give an appropriate object here, which in our case is a tensor category. The tensor category will have to have some finiteness, the fusion category it's called, and have some data that tells you about the invariance. That's called the spherical structure, at least for the SO3. And once we give that, then we can get a field theory. So that's very different from a classical model, like the gauge theory, where we sum over some fluctuating classical fields. Here we just give the quantum theory using the cobordism hypothesis. Okay, so that was proved by Lurie, Hopkins-Lurie in 2 dimensions, and that's a very active field at the moment with Ayala Francis and other people giving different approaches. Okay, so I want to use that to construct a second theory. You see, given a finite group, we have that group algebra, that categorified group algebra, but there's a more common tensor category, which is just the category of representations, where if you have two representations, the tensor product is the tensor product. And so we could contemplate having a theory where, to a point, we attach this tensor category. That satisfies all the conditions needed up here, and so we get a field theory, which I'm calling R sub G. So that doesn't have a classical model. It has a state sum model due to Toraya-Vera. Now, in the case when G is a finite abelian group, if it's abelian, then, the representations that are irreducible are all one-dimensional, and they themselves form a group. That's the Pontryagin dual group, A check. And so a representation is just given by the multiplicity spaces, which is to say it's a vector bundle over A check. And if we tensor representations here, that corresponds to convolutions here. So in other words, this theory, in the abelian case, is a gauge theory. It's the gauge theory for the Pontryagin dual abelian group. So just in the theory of tensor categories, there's a Morita equivalence between these two. In other words, these are isomorphic objects in that three category of tensor categories. And what that means by the cobordism hypothesis is that these two theories are isomorphic. So the theory for G that I get by the classical model of gauge theory and the one I get from the representation are actually isomorphic theories. They're isomorphic, I need the orientation to make the isomorphism. So if we do that in the abelian case, we could look at the space of states on a closed two-manifold. So on the one hand, it's functions on A bundles. On the other hand, it's functions on A check bundles. And in fact, these two groups, these cohomology groups, are themselves Pontryagin dual. That uses the orientation of Y. And the map between them is just the Fourier transform, which is an isomorphism of functions from an abelian group to its Pontryagin dual. So in the abelian case, this is Fourier transform. And we can also see what it does on line operators. Here's the category attached to the circle. In the abelian case, conjugation is trivial, so I just get a bunch of points with A acting. In other words, the vector bundles over here that are equivariant are vector bundles on A cross A check. So this axis is telling me the monodromy around the circle. That's the point I'm at here. And in this axis, we're telling the representation of the centralizer. So the 't Hooft loops are here. Those are the ones where the centralizer acts trivially. The Wilson loops are the ones supported at the identity. And the duality exchanges A and A check, and so it exchanges the Wilson and 't Hooft loops. So that's the usual picture. So this is electromagnetic duality, but we can do it for any finite group G, so this is a non-abelian version of electromagnetic duality for finite groups. Okay. So that's a quick review of this extended field theory. That occurs in many places since the early 90s when that was developed. And what I want to describe today is a kind of different application to lattice models, namely to the two-dimensional Ising model. So let me turn to that. So we're going to look at manifolds that are equipped with a lattice. So I have to tell you what a lattice is. We've already seen that in Ed's talk today, for example. So we just need the one and two-dimensional case. In the one-dimensional case, a lattice is just a finite set of points. So it's just a polygon, in other words, on a circle, or it could be a union of polygons. That's easy. And on a surface, well, it's just an embedded graph. You can read the conditions. Basically, we want that it's a union of polygons. We don't ask that they necessarily be triangles. But we do ask that the closure of each face be a polygon, that the thing doesn't wrap on itself. And also it has to intersect the boundary nicely so that the boundary also gets triangulated. So that's what the definition says. And, well, so there are no loops in there, but faces could share multiple edges. Anyway, it's kind of standard notion of what a lattice is. So we'll be doing the Ising model on compact manifolds instead of in flat space, which is often where it's studied. And so to begin, we'll take the classical case, which is the case where the spins are valued in plus and minus 1, the cyclic group of order 2. And there's a parameter, a positive real number, which is thought of as the inverse temperature. And so there's a function on the group whose values are e to the plus minus beta. We'll use those to weight. And the classical fields in this case are the spins. And so if I have a two-manifold like this, think of a closed one to begin, with a lattice, then we just take functions on the vertices. We take maps from the vertices to plus and minus 1. So that's a choice of spin on each vertex. And now we get a function on the edges, given a configuration of spins, which compares the spins at the two ends, and it just takes the ratio. And so the Ising partition function, if y is closed, says that we sum over all the different configurations, and we weight them by the product over the edges of those weights, depending on the configuration. So that's the classical Ising model. And, well, we can clearly do it more generally. We didn't have to have this finite group plus or minus 1. We could have an arbitrary finite group. And we'll need to know these weights, so we'll need to have a function on the group that will tell us how to construct the weights. And that function, well, we want it to be symmetric in this sense because we're not orienting the edges. So when we take the ratio, we don't have to orient the edges. And basically, the other conditions say the function is positive or non-negative, and its Fourier transform is also non-negative. So those are the conditions on those weight functions. And so we can make the Ising model for an arbitrary group, and a key fact is that this has a symmetry. Namely, if I shift all the weights by a constant g, since the function just depends on the ratio, I don't change it. So it has a symmetry where I just shift by the constant function g. So that's a symmetry. Okay, so here are two interpretations. The first one is very standard, that we get a probability measure on this finite set of configurations. And what happens to that measure? Well, this is the case of high temperature. We get a uniform measure. And so the system is in a kind of random state. On the other hand, at low temperature, the measure ends up being supported at just 2 points where all the spins are equal. In other words, on the two constant functions. Of course, we can take not just the partition function, but the expectation value of a function. So for example, here we can take the correlation function of two spins and average it, and that's called an order operator in the Ising model. The interpretation that I'll use, rather, is a quantum mechanical interpretation, and we'll say it in the same language that we talked about field theories, namely as a map. This time it's a two-dimensional field theory, so of 1 and 2 manifolds, but the manifolds are equipped with a lattice. That's the structure of the manifold. And again, we have a functor, vector spaces. So how does that go? Well, given a closed one manifold, we have to give a vector space. Well, we just take the functions on the fields, same as we did in the finite gauge theory. So that's a vector space. Its size depends on how big this polygon is on the circle, for example. And if we have a Bordism, we can think of a Bordism with a lattice. So it restricts to a lattice on the incoming boundary and on the outgoing boundary. We again get this correspondence diagram of the spins. We take a configuration of spins, we can restrict it to the incoming boundary, we can restrict it to the outgoing boundary. And we again define it by push-pull, only now when we pull back a function, we multiply by this k. That's a kind of integral kernel in this context, or the exponentiated action. And then we sum here over the different configurations. So that fits it into this language of field theory. And in particular, we could look at the Hamiltonian picture, where I start with a one-dimensional configuration, which is just a polygon. I cross it with time, so we get this prism. And well, we get a self-map of this vector space that in condensed matter is called the transfer matrix. You can think of that as e to the minus Hamiltonian, and so it gives you a notion of energy in this model, the eigenvalues of the Hamiltonian. Okay, so what's one of the key properties of this model in the case when A is abelian is this duality of Kramers and Wannier, and we can say it in the following language of cochain complexes. So the configurations are really zero cochains, functions on the vertices with values in A. There's a co-boundary map, and the co-boundary map is nothing but the ratio that we took before. And so there are two functions now on C1. One is the function on the group, these weights. That's a function on the edges. And the other one is just telling us that we're supported on the co-boundaries. In other words, we're taking configurations on vertices and then taking the ratios on edges. And this Ising partition function on a closed surface can be rewritten in those terms as simply an inner product of these two functions on this group. So this is a finite group, C1, and we have these two functions, and we take their inner product in the obvious L2 metric on the group. So that's a way to write the Ising partition function. But once we do that, well, so here's the cochain complex. It has a dual chain complex. These are then Pontryagin dual groups where I take coefficients in the dual group. And in particular, we can take the Fourier transform from functions here to functions here. And one of the basic properties of the Fourier transform is that it's an isometry. And since we express the Ising partition function as an inner product, then that inner product can be re-expressed as the inner Fourier transform of this theta, this function on the group, is now a function on the dual group, A check. And what we get as the Fourier transform of coboundaries, it's not surprising, is we get a function on the co-closed guys. So we don't quite get the same thing. So this is, in other words, it looks like an Ising model for the dual group, except it doesn't quite match. And what happens in the classical case, the cyclic group of order 2, is the Fourier transform is the usual transform that takes the temperature to a kind of transform temperature, exchanges high and low temperature. Okay. So, so there are a few kind of problems with this model that I just want to set up for what we're going to say. So one is that this duality is not quite right. As I said, it's off by the homology groups. We haven't talked about how order and disorder operators map. I didn't even talk about what the disorder operators are, but they don't quite map so cleanly. There's no dual for G non-abelian. I told you about what happens with A abelian, but there isn't the dual when G is non-abelian. And I haven't talked about the low energy states, but I will, and there's a kind of mismatch there. So what I want to talk about is how to use this symmetry. I told you that there's a symmetry group G acting. How to use this symmetry in a strong form to reformulate this model. Okay. So that's going to clear up these issues pretty quickly, and it will also do some more. One is it will give us a prediction for the low energy behavior of this model. Two, it'll give us more general models than were known. And we're eventually going to actually make the whole story as part of topological field theory, and there are higher dimensional versions, which I may or may not have time to say a word about. So let me just make a general comment about symmetry. If we have a symmetry in some problem, you can think of that as a condition, that something is invariant. But a rather stronger form is to spread that over BG, which is data. You somehow you view your object, whatever it is, as sitting over a point. And a strong form of saying that it's invariant under G is data, where you construct some object fibering over BG. Well, what does BG mean? It's some classifying space of the group. But what we mean by that will vary certainly with the context, what kind of model we mean for BG, and what we mean by such a fibering. So in geometry and topology, often this is the Borel quotient, but we might ask that question about, say, invariant cohomology classes or other kinds of things. Or this object might be, say, a category. You might have a group acting on a category, and then you try to say what the group acting on it in the strong form of spreading over BG is. So typically when you do that, there's an obstruction theory. You have to do cell by cell, and you might encounter what in physics would be called anomalies. You encounter obstructions to extending the symmetry. And this usually gives a much richer picture and is a rather powerful technique even for proving theorems, because it converts problems about equivariance, about having symmetry, into problems about parameterized families. All right, so what does that look like in this Ising model? So this is very typically done in field theory. We're just doing the same thing here in this discrete model. So spreading over BG means coupling to a field with values in BG, which is to say coupling to a G bundle. So instead of having our Ising spins, which are functions to the group G on the vertices, functions from the vertices to G, what we do is we give ourselves a background G bundle, I'm calling that Q, over Y, and now we have a section of the G bundle over the vertices. So that's like a gauged linear sigma model, but here the sigma model is just over the vertices. And now we have to extend the theory, which means we have to extend the weights. But the weights, remember, were built from the ratio along an edge of the two spins. And even if they're living in some G torsor in this principal bundle, we still know how to compare because we can parallel transport along the edge. So there's no problem in extending the theory and making this kind of strong form of G invariance. So what about the partition function? Well, now for each background bundle, you get a number. That's the partition function we wrote before. And so now the partition function is a function on the bundles. And if we quantize on a one manifold, then we have to give ourselves a background G bundle on the one manifold. That goes by the name of twisted sectors in some contexts. And so for each background bundle, we get a vector space of states, and so we get a vector bundle over bun G. So those we recognize from our finite group theory. Functions on bun G, that's the vector space that's attached to Y in the three-dimensional gauge theory, and these vector bundles over bun G are the category attached to S in the three-dimensional gauge theory. So in other words, the Ising model is a boundary theory for this finite gauge theory. That's the strong form of saying that it has a symmetry group G. Okay. So after we posted our paper, actually a few weeks ago, we were informed that we were much anticipated in what I'm saying, and in particular, what I'll say at the end, by Pavel Silvera, 16 years ago, it turns out. Okay. So what is a boundary theory? Well, in this axiom system, a boundary theory is a map from the trivial theory to your theory, but we're not considering this gauge theory in 3 dimensions. We have to truncate it. We're only trying to do it in 2 and lower dimensions. And again, the cobordism hypothesis applies. And so if we have these topological boundary theories, it's determined by what happens on a point, and we'll come back to that. But the Ising model is not a topological boundary theory. It's not defined just on manifolds. It's defined on manifolds with a lattice. So we take our gauge theory, which is topological. It just depends on manifolds, but we pull it back to the lattices, and our Ising model now, of course, uses the lattice to define it. So I've already said that for Y closed, if you evaluate this diagram, that you get a function on the bundles. Okay. So what about these line operators? Well, the gauge theory has line operators, and I told you we could have line operators that end on the boundary. And now, if we have this Ising boundary theory, then we can make the line operators, at least the Wilson and 't Hooft operators, with the boundary condition. So for the Wilson operator, I want the path to end on vertices here. And if it ends on vertices, we can write down the Wilson operator. And if we do that, what we're getting is essentially the order operator in the topological theory. So the order operator in the Ising model becomes the Wilson operator in the gauge theory. And similarly, the 't Hooft operator becomes a disorder operator. And for that, the loop has to end in a face. Okay. So all the things I said before are solved by thinking of this as a boundary theory. Now this Kramers-Wanier duality is really part of electromagnetic duality, the one that I told you at the beginning about the gauge theory. And so we can see how that acts on the boundary conditions, and that's the Kramers-Wanier duality. The order and disorder operators, I've said, are Wilson and 't Hooft operators, and those are exchanged by the duality. And now there's a dual for G non-abelian. So I don't have time to describe it here. It's in our paper. But I told you for the gauge theory how to make the dual, which is this theory without a classical model if G is non-abelian. And we can make, similarly, a boundary theory for that with the lattice. Okay. And now I'm going to tell you about the low energy states and what we gain about those. So here's a very general picture. Supposing that we have some kind of space of quantum theories. So these could be quantum field theories. In our case, these are lattice theories, could be string theories. And so we might imagine that they form some moduli space. And now there's a bad locus in there, well, a locus that we want to remove, which are where the phase transitions happen. And in fact, we wanted really from the beginning only to consider gapped systems with an energy gap, quantum systems with an energy gap. And so we should consider these gap systems where we throw out the points where there are phase transitions. So what's left could be thought of as the nice kinds of spaces. It's something we do in geometry all the time. Take some kind of algebraic variety like Calabi-Yau threefolds. We might throw out singular ones and then look at what's left. And the question we usually ask about deformation classes, in this context, pi naught, the path components of what's left, those are called the phases. And so we might ask, what are the possible phases? And So there's an invariant of the phase, which is the low energy effective topological field theory. It might be slightly off from being topological, but that won't enter today. And that low energy effective topological field theory is thought to be a complete invariant of the phase. So if you can calculate that, that's thought to be a complete invariant. Then there's dynamics, which I don't have anything to say about, which is, of course, the renormalization group flow. So here's the picture for the classical case of mu2. This is in plus and minus 1. There's one parameter, that's the beta we started with, which is a positive number. And there's one critical point. And so the complement of the critical points are these two intervals. And if we think of this parameter space, as I said, as the admissible functions on the group. So I define the space of weights by the space of functions on the group that are positive with positive Fourier transform and symmetric under G goes to G inverse. And if we just rescale, we don't change the model. So in this case, we get exactly this space. And notice at the extreme points, what we get are actually characteristic functions of subgroups. In this case, there are two subgroups, the trivial group and the whole group, and we get those. And so the renormalization group flow is meant to flow to those characteristic functions, and that should characterize then the low energy state, as we'll see. So here's the picture for U5, the fifth roots of unity, cyclic group of order 5. Here's the locus where there's a phase transition, and then these unshaded areas are also thought to be gapless theories. So those are thrown out, and then we have these two components left. And notice in this picture, there are 4 extreme points to this convex set. 2 of them correspond to the 2 subgroups. Those live near the gap theories. And then there are these other 2, which don't live near the gap theories. Okay. So we want to apply the full force of this G symmetry. Namely, the Ising model itself is invariant under G, has this G symmetry, so we would expect the low energy topological theory to also have the G symmetry. And in the strong form, that means it has to live as the boundary of this gauge theory. It has to be a boundary theory. And, well, that's a topological boundary theory. And that question is one we can address with the cobordism hypothesis in the framework of these fully extended theories. So what it ends up being is a module over vect, and those modules are classified by a theorem I think originally due to Ostrich. And the classification is simply, well, the irreducible ones are given by a subgroup and possibly a central extension of the subgroup by the circle. So that's a pretty easy theorem, actually, in algebra, and it's telling you what all the possible topological field theories are. And so there's also a classical model for these. And so the prediction is, well, we don't see a way for central extensions to come because these weights are positive real numbers. Central extensions would have to involve negative numbers and complex numbers. And if we assume that that what we get is irreducible, then you would see that the low energy theory is classified by a subgroup of G, and that's symmetry breaking. In other words, for these theories, we would predict that the symmetry breaking classifies. There's nothing more complicated that would happen in the phase as it does in other kinds of models. Okay. So we use the twisted sectors to see what they are. And so in the Ising model, there were 2 different topological field theories one gets. And so here is the high temperature phase. Here's the untwisted sector. Here's the twisted sector. But in the high temperature phase, the thing is totally random. And so there's a unique low energy state in each sector. On the other hand, in the low temperature phase, then the spins tend to align and the symmetry is unbroken. We get the regular representation. That's in the untwisted sector. And in the twisted sector, well, the lowest energy in that sector intuitively will be strictly larger than the low energy here, where they can all be aligned. And so they won't contribute to the low energy field theory. So if we didn't have the twisted sector, you see, we would be missing this one. We'd have a one-dimensional space here and a two-dimensional space here. Okay. So now I want to put this whole theory in the context of extended topological field theory. And actually, that lets us use the cobordism hypothesis and really prove a theorem. So in topology, there are two canonical boundary theories for this gauge theory. Whoops. So remember that in this gauge theory, the boundary theories are given by subgroups. And while there are two canonical choices for a finite group, one is the trivial group. And so in terms of the model, we get a trivialization of the bundle. In terms of this classical model, we would get a trivialization of the bundle wherever we put in that boundary condition. And if I think of it as a module over this categorified group ring, then it's just that algebra, that group ring, as a module over itself. So that we call the regular boundary theory. It's like the regular representation of the group. So that's like a Dirichlet boundary condition. The other canonical subgroup, of course, is the whole group itself. And in that case, there's nothing new on the boundary. It's a kind of free condition. So we call that a Neumann condition. And in terms of a module, that corresponds to an augmentation or a fiber functor for this category. So that's that. So the data we have, in other words, is we have this tensor category, which in our case is the categorified group algebra. We have these two modules, which are these boundary theories, and the Hom between these modules is actually trivial. There's only one-dimensional category of such things, and so that's the domain wall between the two boundary theories, and that's unique in this case. All right. So given that algebraic data, the cobordism hypothesis produces, although we have a classical model in this case as well, this gauge theory, these two boundary theories, and the domain wall between them. And so here's how we're going to do it. So imagine that we have this two-manifold with a lattice, which is what we do for the Ising model. Now we'll construct a Morse function who has critical points of index 0 at the vertices, critical points of index 1 in the edges, and critical point of index 2 for each face. So if we just had the square lattice in the xy plane, the function sine x times sine y would be an example of a function like that. So we can always make a Morse function like that. And now what we do is we color the surface by the points that have, if it's a self-indexing Morse function, then between 0 and 1 we color it red, and between 1 and 2 we color it blue. Red being this Dirichlet boundary condition, the one where we trivialize the bundle, and blue being the free boundary condition. That doesn't look so good at the critical points of index 1, so we cut out little balls around the critical points of index 1. So this red blob you see is around that vertex, and around each vertex there's a red blob like that. So in terms of a classical model, we might have a G bundle, and then the boundary condition is telling us we have a field that trivializes it. That was our original kind of gauged Ising field. So if I want to compute something in the topological field theory, we might take this surface and cross it with an interval and only color the boundary condition at time 0 on this one and not color the other one. And we'll think of all of these disks, the boundaries of those, these circles, as being incoming. And we'll think on the other side of the surface as being outgoing. And if we would evaluate this in the field theory, we would get a map from the tensor product of the vector spaces for each of these circles to the vector space for the surface, the vector space in the gauge theory. Well, it's easy enough to evaluate what this vector space is, because if I take a G bundle and trivialize on these two red intervals, then I just get an element of G, just parallel transport along the disk. And so each of these circles, the vector space is just functions on G. And so in that way, if I plug in the function that we want, then you see we create a state in the gauge theory, and that's precisely what the Ising model does. So in other words, we can write the Ising partition function as a part of topological field theory, completely as a part of topological field theory, once we use this idea of an extended field theory and these boundary theories and domain walls. Okay. So we can also construct loop operators and so on. So in fact, we could do this in higher dimensions. So in other words, it lives entirely in this world of extended topological field theories where we have this powerful cobordism hypothesis, and in fact, more powerful versions that use these boundary theories and domain walls and so on, singularities. So this immediately tells us how to get more general theories, because we don't have to start with vect G. one for the gauge theory. We could start with any nice tensor category with the right finiteness and invariance, and we just need this fiber functor to construct the other boundary theory. And those, again, by Tanakian type theorem, those are given by Hopf algebras. So we could get more general lattice models in 2 dimensions from these Hopf algebras. And now, remember that we have this basic Morita equivalence, this non-abelian electromagnetic duality, between the tensor category behind the gauge theory and the one behind this other theory. And so if we take our quartet of data for the gauge theory and we apply this isomorphism, this Morita equivalence, then we get, Then we get the theory for the representations of G, and the Dirichlet and Neumann, they end up exchanging. So in this way, you see, we're exchanging the blue and the red, and so we're exchanging faces and vertices, and that gets us to our dual triangulation. And we're getting the dual theory. And so what it means is that that applying the cobordism hypothesis in this way for this Ising model viewed now purely in the world of topological field theory, if we do that, then we get a proof, actually, of a rather strong form of this Cramer